Alrighty, so we are going to finish out our topic 3 notes based off of the exploration that y'all did yesterday in Desmos. So you should have been handed a blue foldable from the sub, and it's going to look like this, okay? This is going to be the final product, so let me kind of explain how to fold it. So this is your paper, right? And this has like little boxes across it like this. You're going to fold it in half. Okay, so we're going across this way. You're folding it in half, hamburger style, right? When you open it back up, you should see like the crease down here still with the boxes on the paper, okay? Then you're going to take the left-hand side of the paper and fold it in till it hits the crease, okay? This is like called a shutter fold, right? Then you take the right-hand side of the paper and fold it in till it touches the crease so that it ends up looking like this. Okay, and you don't see anything anymore because it's just the blank side of the blue paper. So then what I want you to do is you're going to fold the top part of it down until it looks like you've got about half and half showing. Okay, then you open it back up and you fold the top part, or the bottom part up, so it looks like about half and half. And when you open it back up, you should have 3 sections just kind of separated by folds, and that is going to be where you cut. So you use your little scissors to cut right there, use your little scissors to cut right there, scissors, scissors, okay? So that's where you're going to cut, not through the whole thing, just so that you have flaps, okay? Hopefully someone near you knows what I'm trying to say and they can help you out with this, because that's the best I can do considering I am not there to explain it. Okay, once you have it folded, you're going to title the flaps according to this over here. Okay, so you'll just write those on. We've got negative f of x, f of negative x, a times f of x, f of bx, f of x minus c, and f of x plus b. So you'll just write those on each flap as the titles. Go ahead and pause it if I'm going too fast. So open the top left flap. It should say negative f of x. So what happens when you have a negative in front of your function? Okay, this is like y'all saw yesterday when the a was negative. A lot of y'all said that it became concave down, right? Or it may became concave up. Regardless though, it changes the concavity of the graph, okay? And the reason it's doing that is because what you are actually performing is a reflection over the x-axis, okay? So when you put that negative in front, what it's doing is it's reflecting the graph. So I'm going to use my black pen here to draw approximately the parent function. Okay, it's just a sketch. I'm going to use my red pen here to show what it looks like when you reflect it across the x-axis. Okay, that's what happens if you have negative f of x. It reflects across the axis and it ends up down there. Okay? So that's why whenever you had the a with the negative, that's why it became concave down, because you were essentially reflecting it across the x-axis. Alrighty? So now, open up the flap right next to it, the one that says f of negative b. That's what happens if you have a negative for your b, right? F of negative, oh, I'm sorry, I said that wrong. F of negative x, but it's what happens if you have f of a negative b, right? A lot of y'all said that nothing happened, okay? It is unnoticeable sometimes, right? The reason why is this is a reflection, still a reflection, but it's across the y-axis, okay? When it's across the y, let's think about what happens. If here's my parent function, and I'm going to reflect it across the y-axis, well, it's still going to be in the exact same location, right? So it is unnoticeable when the axis of symmetry is 0, okay? Now, I will say you do notice it if the vertex is not at the origin, okay? So for example, let me draw a little picture over here. I'm actually going to erase this. I know that you can erase, but I think it'll be easier to see if I erase. So if this was your original function, like something over here, okay, if that has a negative b, it's going to pop up over here, and it will be noticeable. It does not change the concavity. The only thing that changes the concavity is if you have the negative on the outside, but it does reflect it across the y-axis. So sometimes you do notice it, sometimes you don't. You probably didn't yesterday in our little activity because most of our vertexes were close to the origin. Okay, so again, if you have a negative on the inside, that's a reflection across the y-axis. So next flap, open the one that says a f of x. Okay, what you're doing when you have a on the outside, when you're multiplying it by a number, is you're performing a vertical stretch or compression, depending on the number that you use. Okay, so a vertical stretch, what I want you to picture is a rubber band. If you have the parent function here, okay, and I start stretching it, I am pulling up and pulling down. I'm stretching it vertically. Well, that graph is not only going to get narrower, just like rubber band would, but it also might dip a little bit, right? Our vertex might go down a little bit because you are stretching it vertically. Okay, so it's getting narrower, and your vertex might lower a little bit. The main thing there is narrower, okay? Now, that only occurs if a is greater than 1. And really this is the absolute value. So for example, like if we said y is equal to 8x squared. Well, that 8 being greater than 1, that's going to stretch it really, really far. It's going to be really skinny. Okay? The other situation we have is a vertical compression, and that is when it gets wider. And that is when a is in between 0 and 1. So for example, y equals 1/2 x squared, right? 1/2 is in between 0 and 1. When that's happening, you are vertically compressing it. So my arrows are still occurring vertically, so I'm going to push from the top and push from the bottom. So again, picture a rubber band. You just have it sitting on your desk and you start pushing it, well, it's going to then kind of pop out, right? It's going to be going this way, right? If you have a rubber band, here's your normal rubber band. If you start pushing it like this and like this, it's going to kind of go like this, right? It's going to get wider. So when you have a quadratic, the graph is going to get wider. Okay? So when you are multiplying a on the outside, your graph is either going to get narrower or it's going to get wider, depending on if it's a vertical stretch or a vertical compression. Okay? Next one. If you have b, right, we kind of noticed that b was very similar to a, right? That is because this is also a stretch or compression, but it's a horizontal stretch or compression. Okay, so again, let me draw my parent function for you. If I horizontally stretch it, so horizontally be side to side, so if I stretch it out this way, again, picture your rubber band. If you just have a rubber band sitting on your desk and you start stretching it this way, what's it going to look like? It's going to start looking like this, right, because you're pulling it. Well, same thing here. This is going to get wider if you stretch it horizontally, okay? And that occurs when a is in between 0 and 1. So again, an example would be y equals, in parentheses, because right now it's inside, 1/2 x all squared. Okay? There's a difference between the a flap, if you open it up, one is inside the parentheses and one is outside. Okay? Our other option is to compress it horizontally. So again, if you picture that rubber band, if I compress it from the sides, from horizontally, it's going to end up looking like this, right? Because you're pushing in this way. So same thing with this graph. It's going to get skinnier because you are pushing it horizontally. Okay, a horizontal compression. So it's going to get narrower, and that's when a is greater than 1. So again, an example of that would be like y is, in parentheses, 8x and then squared. Okay, so really a and b are kind of like perfect opposites of each other. If you're going to get confused on anything, it's probably going to be a and b and keeping those straight. But luckily you have tools like Desmos to help you. You can just type it in and see what happens. Alrighty, c and d are pretty easy, so that's good. If you have f of x and you're subtracting c, what's happening there is a horizontal compression. No, not compression. No. Translation, sorry. A horizontal translation, which if you learned about translations last year, translation, the SL reminds you of a slide. We're just horizontally sliding our parent function around, okay? So here's the parent function. It is either going to be scooted to the right or to the left, just kind of depends. So if c is greater than 0, that is when it's going to move to the right. Now, I do need to make sure I show you an example of this because it's kind of weird. Notice that the original up here says x minus c, okay? So this would be an example like x minus 4 squared, okay? Y equals x minus 4. So notice we're not multiplying, we're actually subtracting from the x minus 4 squared. So when that happens, it's moving to the right. So if it says minus, it actually moves to the right, like this. I don't know why I did a dotted line, that was weird. Okay, moving to the right. Now, if you have something that is less than 0, like x minus a negative 8 squared, in other words, x plus 8 squared, that's actually moving to the left. Okay, to be going this way. Okay, now because that gets confusing, you honestly just kind of have to start telling yourself to think opposite. So when you have a plus sign, it's moving to the left, which is weird because that's opposite of what we normally do. And when you have a minus sign, it's moving to the right. Minus right, that is not what I meant to say. Minus sign. Okay? Again, it's opposite of what you would think. Usually when we see negative, we think going to the left because that's what the negatives are. But with this horizontal translation, it's the opposite. Okay? So f of x plus d on the outside, that is the exact opposite of the other one. This is a vertical translation. Okay? And this one is what you would expect it to be, which is nice. So if that's my parent function, if d is greater than 0, that means it's going to shift up. It's not going to get wider or skinnier, it's just going to shift up. Okay, and that is when you have a plus sign. That hasn't changed. So an example would be like y equals x squared plus 2. Okay, the other alternative would be for it to be a minus sign, right? And that would be shifting down. Okay, so for example, y equals x squared minus 4. So it would be like down here. Okay, not wider or skinnier like I just drew, which is kind of misleading, but really and truly just shifting up or down. And that can just make you think of like a y-intercept, right? If your y-intercept becomes a 2, then obviously you're shifting up. If it becomes a negative 4, you're shifting down, right? So you can kind of use that as a way to remember it. So what I want to do before we move on from the foldables, I kind of want to put a little bit of a summary on the very front title page, okay? If something is inside the parentheses, okay, like this one and this one, if it's inside the parentheses, something is happening horizontally, okay? This is a horizontal shift. This is a horizontal compression or stretch, okay? If something's happening outside of the parentheses, like the A here or the D here, that is a vertical change, okay? Which makes sense. The ones that are horizontal, something's happening to our x, and x goes from side to side. These, something is happening to the whole function, which is more like y, so that's why it's moving up and down, okay? So just kind of think inside parentheses, horizontal, outside, it's vertical. And really the vertical is what you would think it is, and horizontal is always the opposite. Alrighty, so let's just kind of see how this applies. You're going to want to keep this foldable with you. You actually are going to glue it onto that blank page in your notes packet. There should be glue in your little table caddies. Just stick it on there. You might want to wait until after you do the notes on the back to do that, but you just stick it on there and then it'll be in your notes forever. So it says sketch what each of the graphs below would look like based on the transformations that have occurred. So we're not going to actually do it point by point. We're just going to kind of estimate. So looking at this first function, I have something that's occurred here and something that has occurred here. Well, I know that that minus 3 means down 3. Okay, this plus 2, it's a plus sign, right? So that's opposite of what I would think. So it's actually moving to the left 2. Now there is no A, because if I had an A, it would be right here, and it's not there. There is no B, because if I did, it would be right here. So all that's happening is we're moving to the left 2 and down 3. Well, if my parent function looks something like this, and I'm just trying to perform those two things up there, then I know that I'm going to move left 2, 1, 2, and down 3, 1, 2, 3. So this is where my new vertex would be. And it should be about the same size as the parent function, just in a different location. Okay, so that would be my sketch. You don't need to put the parent function on there. I just did kind of for reference if you want it. So let's look at the next one. This one we have 3 changes that have occurred. We've got up 4, we've got to the right 1, and then we've got this negative, which is on the outside of the parentheses. Since it's on the outside, that means it's been reflected over the x. Okay, so again, I'm going to sketch my parent function just for reference. Okay, that was not a very good one, but you get the point. Okay, so right 1 and up 4. That means my new vertex is right there, but it's been reflected over the x. That just means it is now concave down. Okay, so that's an approximate sketch of my new graph. Okay, number 3 has 3 changes. We've got this -1, so that's down 1. We've got -2, so that's to the right 2. Again, it's opposite of what you'd think. And then we have a 2 here. So nothing's been reflected, but that is on the outside of the parentheses. So that means that this is a vertical stretch. Okay, which I know means it is narrower. Again, you can look at your foldable for this. So right 2 down 1 would be a vertex right here. It has not been flipped, so it's still concave up, but it needs to be a little bit skinnier. Okay, a little bit skinnier. So that would be a good approximation. Okay, I'm not looking for specific points on those. I'm just looking for a general sketch that shows me the multiple pieces of the transformation. Okay, so on these 6, you're not having to sketch, you're just literally writing what has occurred. So on number 1, the only thing that is different from the parent function is that -5. It's outside of the parentheses, so that means it has been shifted down 5. That's all you write. Number 2, this one is inside the parentheses, right? So that means it's a left or right. Since it's minus, that means it has gone to the right 5. Okay. Number 3 has 2 things in one. We've got the -6 and the +4. So that's 2 things. See if you can write them down really fast. Okay. This means that it has gone down 6 and to the left 4. All right, number 4 just has 1 extra number from the parent function, just has that 3. It's on the outside of parentheses, so that means it is a vertical stretch or compression. And because it's a 3, it's not a fractional number, that means it is a vertical stretch. You could even say narrower if you even wanted to ignore the stretch or compression thing. Okay, number 5, we've got 2 things here. We've got a +1 and a 1/3. Feel free to work ahead of me here, just pause it. The 1 inside the parentheses means left 1 unit. The 1/3 means it's a vertical compression because it's a fraction this time, but it's still on the outside, so it's vertical. Okay, which again, if you wanted to, you could say makes it wider. Okay. Last one has everything in there. We've got the 7, we've got the 3, we've got the 2, and we've got a negative sign. We've got 4 things occurring here. Okay. So I'm going to say first, it's been reflected over x. Reflected over the x-axis. Ooh, another room. It has been vertically stretched. Okay, because that's what that 2 means. You can even say by a scale factor of 2. Sometimes we say that, by a scale factor of 2. It has been shifted to the right 3 units. And it has been shifted up 7. Lots of things happening in that one. Alrighty. Just 4 more problems. This is where they want you to write the equation. So number 7 says shift 1 unit to the right and 5 units down. So we're using this original equation of y equals x squared. Anything that's moving left and right happens inside my parentheses. Okay, so I need to open up my parentheses. To the right, that means it's opposite, so -1. Okay, 5 units down. That actually is outside the parentheses, and it's exactly what you'd think. So since it's down, we're going to have a minus sign. That would be your equation. Okay, going across to number 8, again, my original parent function is y equals x squared. So if all these changes have happened to it, I just need to put them into my equation. Vertical stretch by 2. Well, vertical stretch is on the outside of the parentheses, okay? So I've got a 2 on the outside, and reflected across the x-axis. So that's also outside, so negative. There's my equation. Okay, see if y'all could do 9. It's very similar to number 7. Okay, so y equals, it's 4 to the left, so that is inside the parentheses, and it's opposite of what you'd think, so it's plus 4. And 9 units up, that's what I do think it is, so plus 9. Then number 10, reflect across the y-axis, so that's actually occurring on my x, right, in the parentheses. Squared, and then shifted up 10, so that's plus 10 on the outside. Okay? So if you want just kind of like a quick little overview, our original function is y equals x squared, but you could have as much as negative a number, x minus a number squared plus a number. Okay, you could have numbers in all of those places. And I forgot one more. You could have a negative here or a negative here. You could have, this would be your A value, this would be your B value, this would be your C value, and this would be your D value. Okay, so you've got all these different options that could be added on to just the basic parent function of just y equals x squared. Okay, so it's just a matter of plugging in your pieces. This is your A, your B, your C, your D. Alrighty, so don't stress over this too much. This is one thing that the Algebra 2 teachers have told us that they are not super concerned about y'all coming in fully understanding, because they're going to go over it again when you get to Algebra 2, which is in 2 years. But I do want you to have just kind of a brief overview and just kind of an introductory understanding of it. So try to do the homework based off this. Use your notes. Don't overthink it. Don't try to overanalyze it. And hopefully you'll do okay. Homework is due on Monday.